This is video number 2 for section 2.4, and now we're focusing on the vertex form of a quadratic function. Okay, so we've already looked at the standard form, f of x equals ax squared plus bx plus c. You could rewrite this in vertex form as the function f of x equals a times the quantity x minus h squared added with k. And the reason this is called vertex form is because the values of h and k give us the vertex of our parabola. Understand that this relates very closely to our transformation rules from Unit 1. So think of it like this. In our library of functions, we have y equals x squared, which is the most basic parabola that you can have. Its vertex is the point 0, 0, right? Well, we know if we take that equation of y equals x squared and we manipulate it to look more like this, we know that h is going to move all of my points h units to the right, and then k is going to move all of my points k units up, right? So this point of 0, 0 would translate to the point of hk, okay? So an alternative approach to graphing something in standard form is you could first put it into this vertex form. And once you're in vertex form, use your transformation rules to plot your points, all right? So that's what we're going to do here in example 2, okay? We're going to rewrite this function from standard into vertex form, then we're going to graph it, okay? Now to go into vertex form, I'm going to begin by taking the first two terms, so the squared term and the linear term, x squared plus 6x. I'm going to group those together with a plus blank, all in parentheses. And then the constant of 5, I'm going to push that to the outside of the parentheses, followed by a minus blank, okay? And notice one of my blanks is positive, the other is negative. That means they will cancel each other out, provided I put the same number in each blank. And that'll maintain the balance of the overall equation here, okay? All right, so to figure out the number that goes into each spot here, I'm going to use this value of 6, my b value, okay? I will cut it in half. So 6 divided by 2 gives me 3, and then I will square it. This results in 9, and I'll put that in both spots this time. Okay, so you've just completed the square. You've made the parentheses a perfect square trinomial. It now factors to x plus 3 squared, and then minus 4. So there's your vertex form, and you can see that the vertex is the point -3, -4, okay? And you're going to find that this number right here, your x-coordinate, is always -b over 2a, okay? Which matches the equation that we gave for finding the x-coordinate of my vertex in standard form, okay? All right, so let's go ahead and let's plot that vertex right here. And then here's where your transformation rules come into play. So recall, let me graph our parent function. So y equals x squared, it has a point at the origin, 1, 1, -1, 1, 2, 4, -2, 4. Okay, so that's y equals x squared. Okay, well, if I change that equation to y equals x plus 3 squared subtracted by 4, the only thing that's going to happen to my red curve here is it's going to shift the 3 units to the left and the 4 units down, okay? There's no vertical or horizontal stretches or compressions taking place here. So I know now from this vertex point of -3, -4, when I go 1 to the right, I've got to go 1 up. And same when I go 1 to the left, I have to go 1 up, okay? If I were to move from the vertex 2 units right, I have to go 4 units up, just like on the parent function. And then 2 units, when I move to the left, I go 4 up as well. Okay, so here is f of x. All right. Now, what about the intercepts of the function? Well, we can see the x-intercepts pretty easily from our graph, but let's look at how we can find those all algebraically, right? So my y-intercept is nothing more than evaluating the function with a 0 for x. So that's simple enough. That would give me 5, right? I could use either version of the function. I could use the standard form or the vertex form to evaluate when x is 0, and it should give me 5. How about I actually adjust my graph a little bit here to include that point, which is up here, and then I'll reflect it. That just gives me a little bit more accurate parabola now. Okay, and then how about the x-intercepts? Well, you can see the x-intercepts from the graph are at -1 and -5. Well, algebraically, I could have figured those out by taking my vertex form, setting it equal to 0. So 0 is equal to x plus 3 squared, subtracted by 4. There's a couple ways you can solve that. To me, the easiest way would be add 4 over to the other side. And then I'm going to square root both sides. That'll give me plus or minus 2 is equal to x plus 3. And then I can just subtract 3 from both sides. Now, if that were a positive 2, 2 minus 3 is going to give me x equals -1. And -2 minus 3 would give me -5. So that's algebraically how you can find your x-intercepts using the vertex form. Okay. All right, example 3 is going to look very similar to example 2 with one exception, okay? So now our function is f of x equals 2x squared plus 8x plus 5. We're going to put it in vertex form and graph. What makes this one a little bit more challenging is the a value of 2, okay? The fact that that is a 2 is a bit of a problem because if you recall, notice what's in red here, my leading coefficient has to be 1 in order for me to use completing the square. All right, so here's how we're going to handle that. I'm going to take the function and I'm going to factor that 2 out front, but I'm only going to do it for the first 2 terms. So notice inside the parentheses, I now have x squared and I have 4x, okay? X squared and 4x, okay? Plus my blank, and then I'm going to shove the 5 to the outside of the parentheses. Notice the 5 stays the same because it's not being touched by the 2 that I factored out in front, okay? Then I'll also put in my minus blank. All right, so at this point, you're going to use this value of 4 to complete the square. Half of 4 is 2, and 2 squared is 4. So you're going to put a 4 in that spot, but then here's where students always go wrong. The second blank will not be a 4. Technically, you didn't add 4 into this equation right now. You technically added 4 times 2 in, which really means you need an 8 over here to balance everything out. Okay, so watch out for that. Now we can factor 2 times the quantity x plus 2 squared subtracted by 3. There's our vertex form, and now I can tell you my vertex is the point of -2, -3. So let's go ahead and plot that right there. Okay, now in terms of transformation rules, notice since the a value of this function is 2, that's going to have a vertical stretch effect on my function. So normally from the vertex on our parent function, we move right 1 and up 1. But because of that 2 for the a value, when I move right 1, I now have to move 2 units up. And same thing when I move left 1, I move 2 units up. Okay. What about if I were to move 2 units to the right from the vertex? Normally I would go 4 up. Well, now that vertical movement doubles to 8 units. Okay, so that's going to take me way up here to 5. Same thing if I move 2 units to the left. Normally I would go 4 up on the parent function. This time I double that movement to 8 units. And here is my parabola. Okay. All right, in terms of intercepts, y-intercept really easy. You can see from the graph it's at 5. That's also found by f of 0 equals 5. X-intercepts not so easy to find this time, just by looking at the graph. Okay, so here's how I would do it with the standard or the vertex form. I would set the vertex form equal to 0. I would add 3 and divide by 2. That'll take me to 3 halves equals x plus 2 squared. Then I would square root both sides. Now the square root of 3 halves is not an integer. I would have to approximate that. It's approximately 1.22. Put a plus or minus in there. So that's approximately equal to x plus 2. Then I'll subtract 2 from both sides. And that would give me x to be approximately negative 0.78 and negative 3.22. Now see if those two values appear to match the graph. So negative 0.78 sure does. Negative 3.22 sure does. Okay. All right, now last example here. Going to kind of switch gears just a bit. I want to determine the quadratic function for a parabola whose vertex is 2, 1, and whose y-intercept is 5. Okay, so here's a situation where I'm given some information about my parabola, and I just want to come up with an equation to match it. All right. Think about the info that you're given. The fact that you are given a vertex, it's giving you an h value and a k value. And this y-intercept of 5, it's like another random point on the graph. That's the point 0, 5. And we can think of those as x and y values. So if I'm working with vertex form of a parabola, notice I have a number to plug in for every variable of that form except for the a value. Okay, so I can plug in 5 for y. I'll leave a as is. I can plug in 0 for x. I can plug in 2 for h. I can plug in 1 for k. And now I solve this for a. That's going to give me 5 is equal to 4a plus 1, or 4 is equal to 4a. A is equal to 1. And think about A again. A controls a couple things for your parabola. It controls your direction of opening, and it controls the width, because it affects a vertical stretch or compression taking place. So think, based on the givens, if you know your vertex is 2, 1, and you know your y-intercept is 5, those two parameters are defining a set width and direction of opening for the parabola. So we're just using that information to determine what a value is needed to match that width. Okay. Once we have that a value, we can write our equation. Y equals a value of 1 multiplied by x minus my x-coordinate of the vertex squared plus my y-coordinate of the vertex. So vertex form is very useful for being able to write an equation given some parameters of the parabola.